Hello everyone. What we'd like to do in this video is we're going to start proving trig identities. Don't let that word prove scare you. All we're doing here is just an exercise in massaging. What we're going to do here is we just want to show that one trig expression is equivalent to another trig expression. These are the type of exercises that I think are really beneficial. Think of these as these type of exercises where you do some sort of problem. You get to the end of the problem and you got your answer. Then you look in the back of the book and you say, "Oh, that doesn't look like my answer. Are our answers equivalent? Are they the same?" Well, you got to show that they're the same. So what are you going to do? You're going to massage your answer to look like the book's answer, or you could massage your book's answer to look like your answer, basically showing that these two answers are equivalent. That's what we're doing here, an exercise in massaging. Let me show you. So these type of exercises are really fun. They're a little bit puzzly. You have some freedom, but overall, they're just really fun. So, as our first example, let's say that maybe you're doing some sort of problem and your answer is cosine squared of x over the sine of x. But maybe in the back of the book it says cosecant of x minus sine of x. And maybe you're saying, oh, I did all this hard work and these answers are different. But maybe your answer is right. So what is your goal? Your goal is to show that these are equivalent. We are going to show that these are equivalent. Okay. So what I'm going to do is we're going to use some lingo I'll use throughout this problem, or through all these problems, is when I'm trying to show that these are equivalent, there's a left-hand side and a right-hand side. I'll abbreviate the left-hand side is LHS, and the right-hand side, we'll call it the RHS for right-hand side. Our goal is to make left-hand side equal to the right-hand side, or show that the right-hand side is equal to the left-hand side just by massaging. Now, so you have to pick one side. So you can't start with this equation. You can't just like multiply both sides by sine. You can't start with the equation because you're trying to show that this is true. All you can do is start with one of the sides and massage it to make it look like the other. The question is which side to start with? Well, it's going to be different for every problem. Sometimes, I guess, usually what I'm going to try and do is pick the side that looks more complicated. Sometimes they'll both look pretty complicated. Just pick one side, start working with it, and see if you can make it look like the other side. So for right now, let's start with the left-hand side on this problem. Let's start with the left-hand side. So we have a cosine squared of x all over sine of x. Okay, I have to think about something to do to this. What can we do? Okay, well, there's only one thing that's screaming at me to try here. What's yelling at me is I have a trig function being squared. Whenever you see a trig function being squared, you got to be thinking to yourself, I might want to use a Pythagorean identity. That's exactly what we're going to want to do. That's exactly what we're going to want to do here. We're going to want to remember that sine squared of x plus cosine squared of x is equal to 1. So this cosine squared, if I subtract sine squared from both sides, cosine squared of x is equivalent to a 1 minus sine squared of x. So this might be a nice substitution to make. So let's see what happens. Okay, so now we have a 1 minus sine squared of x all over sine of x, making that substitution. Okay, usually, when you're looking, I'm trying to make this look like the right-hand side. So hopefully it's giving you some ideas of what to do here. I mean, what's great about turning this cosine squared into a 1 minus sine squared is now I have a subtraction sign, which is something I'm trying to get. Okay, what to do from here? Well, I have 1 minus sine squared. I'm dividing it by sine. So I need to divide. I can divide all the pieces by sine. Or I can distribute the sine of x to each of the pieces. So this is equivalent to 1 over sine of x. 1 over sine of x minus a sine squared of x all over sine of x. And now let's try to simplify. 1 over sine, well, that's the same thing as cosecant of x. And over here, we can cancel out one copy of sine. So minus sine of x. And what do you know? It's the right-hand side. It's the right-hand side. This is equivalent to the right-hand side. And we're done. I showed that the left-hand side is equivalent to the right-hand side. So are these equal? Yes! Yes, they are equal. Get rid of that question mark. We're finished. We've done the proof. How do we conclude a proof, or what do I like to do when we conclude a proof? It's very common to write a box, kind of fill it in. Finished with the problem. I showed that the left-hand side is the same as the right-hand side. Now, for this specific problem, did we have to choose the left-hand side to start with? No, we could have started with the right-hand side. In some of these problems, you might start with one side, start massaging it, and get a little lost and not really getting anywhere. You may want to start over and just start with working with the right-hand side. So let's do this problem another way. Let's say maybe you wanted to work with the right-hand side. So maybe we started with the right-hand side. So we have a cosecant of x minus a sine of x. Maybe we started with this. Okay, I want to make it look like the left-hand side, but what to do here? Well, the only thing that's screaming for me to at least try is write this in terms of sines and cosines. Cosecant is the same thing as 1 over sine of x minus a sine of x. Okay. So now what's screaming at me to try here is find a common denominator. Let's find a common denominator. So let's hit this with a sine of x over sine of x. Okay. So in the numerator, we'll have a 1 minus a sine squared of x. And in the bottom, we'll have our common denominator of sine of x. Okay. Well, where to go from here? Well, I don't know if you can smell 1 minus sine squared. That smells a lot like cosine squared. Remember, sine squared of x plus cosine squared of x is equal to 1. So if I subtract sine squared from both sides, cosine squared is equivalent to 1 minus sine squared. This is the same thing. This is the same thing as cosine squared of x all over sine of x. And what do you know? What do you know? That is the left-hand side. The left-hand side. I showed that the right-hand side is equivalent to the left-hand side, so we're finished. We are done with the problem. Do you have to do it both ways? No, you only have to do it one way. You just pick one side and show it's the same as the other. Equivalently, you could take the right-hand side and show that it's equal to the left-hand side. You don't have to show both, you just need to show one. Sometimes one is easier than the other. Sometimes they're, I would say, equally as easy. Was this way easier than the other one? I don't know, I would say they're probably both equivalent. Okay, let's try another problem. Let's try another problem. Okay. Let's say that we want to show that, how about sine of x plus cosine of x squared is equivalent. We want to show this. We want to show that's equivalent to 1 plus 2 sine of x times cosine of x. Okay. Go ahead and maybe pause the video and try this on your own. Okay, let's do it. Which side to start with? Which side to start with? Well, looking at the right-hand side, I don't really see much that we can do here. I can't find any fractions to add. I don't see any nice identities to try and use here. But the left-hand side, ooh, it's hurting. It's yelling so loud at us. It's yelling us so loud for us to have something to do with the left-hand side. It's saying, hey, you can expand me. You can expand me. So that's what we're going to do. Let's start with the left-hand side. Okay, the left-hand side is screaming for us to try something. Is it going to lead us somewhere? I don't know. We're just going to try, and let's see what happens. Let's FOIL this out. So this is the same thing as sine of x plus cosine of x times a sine of x plus a cosine of x. And let's expand this. Okay. So we'll get a sine of x times a sine of x. So we'll get a sine of x squared. We're going to get a sine of x times a cosine of x. Okay. And then we're going to get also a cosine of x times sine of x. Okay. Plus, we're going to get a cosine times a cosine. We're going to get a cosine squared of x. Okay. So we have a sine squared of x plus, well, order of multiplication doesn't matter, so these are like terms. So we have 2 sine of x cosine of x, or that'd be equivalent to writing 2 cosine of x times sine of x, plus a cosine squared of x. Now we should be getting very excited. We should be getting very excited here because we got sine squareds, we got cosine squareds, we got Pythagorean identities here. But specifically, we got both pieces. We got sine squared and cosine squared. This smells like 1. This smells like 1. Sine squared plus cosine squared is 1. Change the order of addition. Sine squared plus cosine squared, that's just 1. That's just 1. 1 plus 2 sine of x times cosine of x. And what do you know? What do you know? It's the right-hand side. It's the right-hand side. And we're finished. And we're finished. And we're finished. We showed that the left-hand side is the same as the right-hand side. Okay. So in this case here, it was so much more convenient for us to start with the left-hand side and show it's the same as the right-hand side. It would have been very tricky for us to start with the right-hand side and show it's the left-hand side. Okay. Let's do another one. Let's do another one. It's doing tons of examples. This is a great time to be creative, play around, have a lot of fun. Okay. Here's a good one to mess around with. Okay. Let's say we have sine squared of x is equal to, or we want to show that it's equal to, tan squared of x all over, how about tan squared of x plus 1. Okay, maybe go ahead and pause the video and see if you can show that these two trig expressions are equivalent. Okay, let's do it. What side to start with? Well, looking at the left-hand side, maybe you're a little bit excited that we have a sine squared, and we can make that sine squared, I don't know, a 1 minus cosine squared, but I don't really see where that's going to lead us. So I don't think working with the left-hand side is going to be our best option here. The right-hand side seems like there's a lot more going on, so I think I'm going to at least try to mess around with the right-hand side and see where this leads us. So let's start with the right-hand side. We have tan squared of x all over a tan squared of x plus 1. Okay, but what to do with this? What to do with this? Well, again, I'm seeing trig functions being squared. It's yelling at me, Pythagorean identities, Pythagorean identities. Well, let's take a look at them. If you don't remember what the Pythagorean identity that has a tangent in it, all you got to remember is that sine squared of x plus cosine squared of x is equal to 1. This is just the Pythagorean theorem on the unit circle. I need a tan squared to show up. We need a tan squared to show up. So just divide everything by what? I need a sine over cosine by cosine squared of x. Cosine squared of x. Only do this exercise if you don't have it memorized. But this is how I got to memorize. Sine squared over cosine squared, that's a tan squared. That's a tan squared of x. Cosine squared over cosine squared is 1. 1 over cosine squared, this is the same thing as secant squared of x. Maybe something to try here. Well, the bottom, the denominator here is the same thing as secant squared. So let's mess around with that. We have a tan squared of x. The denominator is a secant squared of x. Now, what route to take from here is really completely up to you. One good thing to try if you get lost or don't know what to do is write everything in terms of sines and cosines. So, this is where we can really be creative. Maybe the approach you say is, sines and cosines, why not? Tan squared is the same as sine squared over cosine squared all over secant squared is the same thing as 1 over cosine squared of x. I have this fraction divided by this fraction. We can flip and multiply. So it looks like we'll get a sine squared of x all over a cosine squared of x times whoosh, cosine squared of x all over 1. And what do you know? What do you know? The cosine squareds cancel, and we're just left with sine squared of x. It's the left-hand side, which is equal to, this is equal to the left-hand side. We showed that the right-hand side is the same as the left-hand side. We're finished. We're finished. We massaged one side to look like the other side. Okay, this may not be the route that you've taken. Maybe you saw something different to do here. You know, this is, again, where we can have fun and be creative. Maybe, you know, what else could have you done here? I mean, you could have said, oh, well, this is the same thing as tan squared of x. And you could have said, well, secant squared, that's 1 over secant squared. Well, 1 over secant squared is the same thing as cosine squared of x. So you could have written this expression like this. And you could have said, oh, well, tan squared is the same as sine squared of x all over cosine squared of x times that extra cosine squared of x. And look, those will cancel. And we're right back to sine squared. We're right back to the left-hand side. Okay, you could have taken that approach. Maybe another thing you could have done here is, well, maybe you wrote everything in terms of secants. Well, I don't know. Why not? Tan squared, well, tan squared would be the same thing as secant squared minus 1. So maybe you said that this is the same thing as secant squared of x minus 1 all over secant squared of x. I don't know, maybe this is where your playing around led you. Okay, well, what would I have done from here? Well, the only thing that's screaming to try here is maybe distribute the secant squared to these two pieces. So this would be the same thing as secant squared of x all over secant squared of x minus a 1 over secant squared of x. Okay, well, these will cancel, so we'll get a 1 minus 1 over secant squared is the same thing as cosine squared of x. And well, 1 minus cosine squared, 1 minus cosine squared, 1 minus cosine squared is the same thing as sine squared. Which is, again, the same thing as the left-hand side. So a couple different approaches to take here, but we all got to the same place. Was one better than the other? Well, I wouldn't say so. But again, it's just playing around, trying to make one side look like the other side. Okay, let's do more examples. Just get tons of practice. Okay, what I actually want to do in this next example is illustrate a trick. You gotta get lost, you don't really know what to do. There's some tricks that we could use. Okay, so I'm gonna title this one "Some Tricks." Some tricks we can use. Okay, let's say we want to show that 1 minus sine of x all over cosine of x is equivalent to, how about cosine of x all over a 1 plus sine of x. We want to show that these are the same. Okay, well, I mean, what could we do here? Maybe if we're just playing around, maybe we want to mess around with the left-hand side. I don't know. Maybe we start with the left-hand side. At least I could see with the left-hand side that I could distribute this cosine of x to both of the pieces in the numerator. As of right now, I don't really see too much I can do with the right-hand side without introducing something new, which I'll show you in just a second. But let's say we mess around with the left-hand side, and we have a 1 minus sine of x all over a cosine of x. And you're thinking, oh, well, the only thing I can maybe see to do here is distribute this cosine. So 1 over cosine of x minus a sine of x all over cosine of x. Okay, well, 1 over cosine, I don't know, that's the same thing as what, secant. And sine over cosine is the same thing as tangent. But now we're kind of stuck. Like, what to do from here? I don't really know what to do. I mean, if any of these pieces were squared, that might be something to try. We could use a Pythagorean identity. Unfortunately, they're not being squared. I mean, the only thing I could do if we started with this is to write it in terms of sines and cosines, but that would just lead us back this way. So there's nothing to do here. I can't really see a good way to go from here. I'm kind of wishing we had things that were squared to use some Pythagorean identities. So let's kind of go back to the drawing board. What can we do here? Well, the trick for these type of problems, specifically if you see like a 1 minus sign, a 1 plus sign, or a 1 minus cosine, a 1 plus cosine, and you kind of wish we had pieces that were squared to use a Pythagorean identity, we're going to try using conjugates, and that's the trick here. So we introduce conjugates. Now, if you don't remember what a conjugate is, they're very useful. You'll see them pop up in calculus. Okay, hopefully maybe you've seen them pop up. I think I first introduced conjugates, I think in Math 98, and we're solving like radical equations. You know, equations with roots in them. Well, a conjugate, let's say if we have something like, I don't know, if we have something like A plus B, its conjugate would be A minus B. Or if we have something like C minus D, its conjugate would be C plus D. So if you have an expression that has an addition sign, its conjugate would be the same expression with a minus sign. Or if you had something with a minus sign, its conjugate would be the same thing, just with a plus sign. And why are conjugates useful? Conjugates are useful because of the difference of squares pattern. They have a great relationship when you multiply something by its conjugate. For example, if we have something like A plus B and we multiply by its conjugate A minus B, well, if you FOIL this out, A times A, we'll get an A squared. We'll get an A times a negative B, or a negative AB. Plus, we get a B times an A. And then a B times a negative B squared. Well, what's so great here is that, you know, this is AB. B times A, that's the same as A times B. Well, the O and the I in FOIL with conjugates will always cancel each other out, and you'll just be left with an A squared minus B squared. So that's why they're useful, this difference of squares pattern. I'm kind of forcing a difference of squares pattern to happen so I can get something squared, and that'll help us to get a Pythagorean identity to pop out. Okay, so with this specific problem, we can start with the left-hand side or the right-hand side and try to use a conjugate trick. So we already started with the left-hand side, so let's say we continue working with the left-hand side. So we didn't get anywhere by distributing this cosine. But when I see a 1 minus sign, I wish it was 1 minus sine squared. Well, we'll use the best trick in the math book, and we'll cleverly multiply this by 1, but we'll do 1 plus sine of x all over a 1 plus sine of x. So I'm going to cleverly multiply by 1, but I'm going to do it with a 1 plus sign. Okay, this is going to be helpful, because when I multiply these fractions together, I get a 1 minus sine of x times a 1 plus sine of x. All over, we have a cosine of x times a 1 plus sine of x. Okay. I mean, don't cancel these out. You just be right back to where you started. But the whole point here is I want to multiply these out. So I'm going to do a 1 times a 1. So I'll get a 1 squared times a 1 plus sine, so we'll just get a sine of x. Okay, I'm showing a lot of gory detail here in this first one. And then we're going to get a negative sine times a 1, so we'll get a minus sine of x. Plus a negative sine times a sine, we're going to get a minus sine squared of x, minus sine squared of x. All over, we'll have a cosine of x times the 1 plus sine of x. Okay, well notice, because, you know, these are conjugates, that the O and the I in FOIL cancel each other out, and we're just left with this 1 minus sine squared. That's what we want to happen. So I'm kind of running out of some room here, so I'm going to go ahead and erase these middle pieces. This just turns into a 1 minus sine squared. A 1 minus sine squared of x, which is great because 1 minus sine squared smells like cosine squared. It's the same thing. So kind of moving this up over here. 1 minus sine squared is the same thing as cosine squared of x. We get a cosine squared of x. All over, we have a cosine of x times a 1 plus sine of x. Cool. Well, look, this is great because one of these factors of cosine cancel. So we're just left with now the cosine of x all over 1 plus sine of x. And what do you know? It's the same. It's the same as the right-hand side. It's equivalent to the right-hand side. So we just showed that the left-hand side is the same as the right-hand side. It just took some clever multiplication of 1, but, you know, we wanted that multiplication of 1 to give us a 1 minus sine squared so we could use a Pythagorean identity. So we're finished. Notice that you could have done the same trick with starting with the right-hand side. So maybe we could do that really quick. Maybe this is a good time to practice it. Maybe start with the right-hand side, use the conjugate trick, and show it's the left-hand side. Maybe a good time to pause the video and try that. Okay, let's start with the right-hand side. We get a cosine of x over a 1 plus sine of x. Okay, I wish I had a 1 minus sine squared. So let's multiply by the conjugate. How about a 1 minus sine of x? All over a 1 minus sine of x. Okay. In the numerator, we'll get a cosine of x times a 1 minus sine of x. Don't forget those parentheses. Half of the mistakes I see in math come from just not being paranoid enough with parentheses. And now when the denominators multiply, that's that difference of squares pattern, we're going to get a 1 squared, or just a 1, minus a sine squared of x. But 1 minus sine squared is the same thing as cosine squared. So we'll have a cosine of x times a 1 minus sine of x. The bottom is the same thing, using that Pythagorean identity, is the same thing as cosine squared of x. Well, look, these cancel. And we're left with a 1 minus sine of x all over cosine of x, which is equivalent to the left-hand side. And we're finished. How fun is this? Okay. So sometimes introducing a conjugate can be super useful. Okay. Let's do another example. Okay. Let's say for another example, let's say that we want to show that 1 plus secant of x, that 1 plus secant of x all over secant of x is equivalent to, again we're trying to show this, is equivalent to sine squared of x all over 1 minus cosine of x. So there are a couple tricks I want to kind of illustrate with this example, but I think it might be a good idea just to pause the video, play around with it a little bit yourself before we do it together. Okay, let's just mess around. What can we do? Well, maybe you decide to start with the left-hand side. Let's see what the left-hand side does. The left-hand side. Well, the left-hand side, 1 plus, you might have started with the right-hand side, but I don't know, let's just say we mess around with the left-hand side first. Okay, well, at least what I can think to maybe try and do here is, well, I could maybe distribute this secant to each piece. So maybe you think to say, oh, this is the same thing as 1 over the secant of x plus the secant of x all over the secant of x, kind of just undoing the fraction addition. Well, 1 over secant is the same thing as cosine of x, and secant over secant is 1. So we have cosine of x plus 1. But how are we going to make that look like a sine squared of x over a 1 minus cosine of x? Well, kind of stuck here. Kind of stuck. Don't really know where to go from here. Another common thing, another good trick to sometimes try is you can actually just massage both sides to be the same thing, and that would be another way to show them they're equivalent. So the left-hand side, the best I could do with it, kind of just simplifying the left-hand side. The left-hand side at least simplifies to a cosine of x plus 1. Maybe you could try to massage the right-hand side to also look like a cosine of x plus 1, which would be another way to show that these are equivalent. So we kind of got stuck. We've hit a roadblock. So maybe we switch to look at the right-hand side. Okay. What can we do with the right-hand side? Well, maybe I'll give you a couple different ways to think about the right-hand side. Okay, well, let's write it out. Sine squared of x over a 1 minus cosine of x. Okay, you could maybe introduce a conjugate here, but I already see a sine squared, so I might just try to use a Pythagorean identity right off the bat. The sine squared is at least begging me to at least maybe try to replace that with a 1 minus cosine squared of x all over a 1 minus cosine of x. Okay. Is this going to be helpful? Well, here's a nice trick that is oftentimes useful. You can oftentimes factor. So I'm hoping that you can see that this numerator here can factor. It's a difference of squares. This is like a 1 squared minus cosine squared. So that's the same thing as a 1 minus cosine of x times a 1 plus cosine of x. So, I'm getting the scent, I'm getting that whiff of a difference of squares, that a squared minus b squared is equivalent to a minus b times a plus b. That's what I've used here. That glare, it's so bad. It's so bad. Just remember that a squared minus b squared is equal to a minus b times a plus b. Is that a little bit better? Beautiful. Difference of squares, that's what I've done here. Okay, all over a 1 minus cosine of x. Well, what's great here is that this factor of 1 minus cosine cancel out, and now we're left with a 1 plus cosine of x. I've massaged the left-hand side to be a cosine of x plus 1. I've massaged the right-hand side to be the same thing as a cosine of x plus 1. So I showed that the left and right-hand side simplify to the same thing, which means that they are the same thing. So we've just shown here that the left-hand side is equal to the right-hand side. And we're finished. How fun. How fun. So there are two good tricks in this problem. One, you don't always have to make the left-hand side look, you don't have to always massage this directly to look like this, or you don't have to massage this to look directly like this. You can try to simplify the left-hand side and the right-hand side to an equivalent expression, which means that they would be the same. That's one good trick to sometimes use. Another trick we should notice in this problem is sometimes factoring can also be very useful here. Okay, let's just do some more problems. Let's do some more problems. Okay. Tons more practice. Tons more fun. Okay. Let's say that we have the tangent of x plus the cotangent of x, and we want to show that this is the same thing as how about secant of x times cosecant of x. Go ahead and pause the video and give this one a shot on your own. Okay. Let's see, what can we do here? Well, I think we could attempt to work with either side here. I'm going to actually choose to work with the left-hand side here. I'm noticing that I could write these in terms of sines and cosines, and I might be able to find a common denominator. So at least the left-hand side is screaming for more for me to do here. So let's start there. Let's see what the left-hand side has to tell us. Okay, the left-hand side, we have a tangent of x plus a cotangent of x. Tangent is the same thing as sine of x all over cosine of x, plus cotangent is the same thing as cosine of x all over sine of x. Okay. So let's try and find a common denominator. So the common denominator will be a cosine times sine. So this side needs an extra copy of cosine. And this needs an extra copy of sine. Okay, so what are we going to get here? Oh, I'm going to get a sine squared plus a cosine squared in the numerator all over our common denominator of sine of x times the cosine of x. Well, the sine squared plus cosine squared is just 1, so this is the same thing as 1 all over the sine of x times the cosine of x. Okay, let's say, for example, that you got stuck here, and you don't know how to maybe make this look like the right-hand side. Okay, I'll show you something you could do. If you get stuck here, maybe saying, I don't know where else to go from here, maybe then you go, oh, well, let's look at the right-hand side. Let's look at the right-hand side now. This is just an option. Well, the right-hand side, we have a secant of x times a cosecant of x. Well, secant of x is the same thing as 1 over cosine of x. And cosecant is the same thing as 1 over sine of x. But when these multiply, you're just going to get a 1 over cosine of x times a sine of x, which is equivalent. They both simplify to the same thing. So we're done here. We're done here. We have that the left-hand side is equal to the right-hand side. Or maybe you realize that I could have gone directly from here to here. A good way to see what this is the same thing as 1 times 1. This is undoing the fraction of multiplication. This is 1 over sine of x. 1 over sine of x times 1 over cosine of x. 1 over sine is the same thing as cosecant of x. 1 over cosine is the same as sine of x. I'm sorry, secant. Which is exactly what the right-hand side is if we flip the order of multiplication. So either way, whether you recognize you could have turned this into a cosecant times secant, or maybe you got stuck here and then massaged the right-hand side to an equivalent expression. Either way, we've shown that the left-hand side is the same as the right-hand side. Fun. Okay. Let's try another one. Okay, let's say that we have sine squared of x plus 4 times sine of x plus 3 all over the cosine squared of x, and we want to show that this is equivalent. We want to show that this is equivalent to 3 plus sine of x all over a 1 minus sine of x. Go ahead and pause the video and see if you can show that these two trig expressions are equivalent. Okay, let's do it. Okay, I think there are a couple great ways we could approach this one. Let's say we start with the left-hand side. Okay. Well, what we could do with the left-hand side, let's go ahead and write it, I guess. Sine squared of x plus 4 sine of x plus 3 all over cosine squared of x is to notice that the numerator here is quadratic in form. If you have trouble seeing that, notice if we make the substitution, y equals sine of x. Well, then this whole numerator just becomes a y squared plus a 4y plus a 3. So it's quadratic in form, and we can factor this. So this will factor to, let's see, I need the factors of 3 that add to 4. So I think a 1 and a 3 would work. Okay, so if I bring my y back, this is the same thing as sine of x plus 1 times sine of x plus 3. So this numerator factors very nicely. The numerator factors to a sine, back to blue. The numerator factors to a sine of x plus 1 times a sine of x plus 3. Okay. So that's just the numerator. Okay, well, I don't really know how having a cosine squared in the bottom is going to help us, but cosine squared, since I have like this 1 plus sine here, it's kind of begging me to turn this and make this in terms of sine by saying that cosine squared is the same thing as 1 minus sine squared of x. Well, what's great is 1 minus sine squared, that's another difference of squares pattern, and we can factor it. So we have a sine of x plus 1 times a sine of x plus 3. The denominator will factor to a 1 minus sine of x times a 1 plus sine of x. Okay. Well, this is great news. It's almost just melting before our eyes that the 1 plus signs cancel, and we're just left with sine of x plus 3 all over a 1 minus sine of x. And what do you know? That's the same thing as the right-hand side. And so we are finished. So, done. Finished. For this problem, you didn't even have to start with the left-hand side if you didn't want to. We could have actually started with the right-hand side. Maybe that's the approach you took. So maybe just a different way to think about this problem is maybe starting with the right-hand side and maybe noticing a conjugate trick might have been useful. So maybe you started with the right-hand side. The right-hand side. Okay, the right-hand side is a 3 plus a sine of x all over a 1 minus sine of x. Maybe you're like, I don't really know much to do with this, but seeing this 1 minus sign might be begging you to try to introduce a 1 plus sign. So maybe you thought to maybe try to use a conjugate here. Okay. So what's going to happen? Well, I have a 3 plus sign and a 1 plus sign. Well, you might think to FOIL that out, specifically when you're looking at the numerator for what we're trying to get it to look like. Well, if we were to expand this, what are we going to get? We're going to get a 3. We're going to get a 3 plus a 3 sine of x. We're going to get a 3 sine of x plus an extra sine of x, so we'll have a total of 4 sine of x. And then a sine of x times a sine of x, we get a sine squared of x. Okay? That's how the numerator will expand. And the bottom, this is a difference of squares. If you expand this, that's going to be a 1 squared minus a sine squared of x, or just a 1 minus sine squared. But 1 minus sine squared, that's the same thing as cosine squared of x, which is exactly what the left-hand side is. This is equivalent to the left-hand side, and we're finished. So either approach, you started with the left-hand side, made it look like the right-hand side, or starting with the right-hand side and making it look the left-hand side, we were able to do it either way in this example here. Except starting with this side, we needed to use a conjugate trick to make it work. Fun. Okay. Let's see. What else can we try? Okay, here's a couple more good examples. let's say, it's another example. Let's say we have the cotangent of negative alpha times the cosine of negative alpha plus the sine of negative alpha. Maybe we want to show that this is equivalent to a negative cosecant of alpha. Maybe go ahead and pause the video and try this on your own before we do it together. Let's get this a little bit out of the glare. Okay, this is what we're trying to show. Okay, let's go ahead and get started. What would I do here? I mean, the left-hand side, there's so much more to do on the left-hand side. So I think that's where I'm going to go ahead and start. Let's start with the left-hand side. Let's start with the left-hand side. And I'm trying to make the left-hand side blue. Okay, so we have a cotangent of negative alpha times the cosine of negative alpha plus the sine of negative alpha. Okay. Since I'm seeing all these negatives inside of trig functions, we may want to think about the even and odd properties of them. Okay, I do have a cotangent here, so if you don't remember the even and odd properties of like cotangent, secant, cosecant, or tangent, just remember the even and odd properties of sine and cosine, and just remember that you can write any trig function in terms of sines and cosines. So I would start by writing cotangent. Cotangent is equivalent to the cosine of negative alpha over the sine of negative alpha times, we still have that cosine of negative alpha plus the sine of negative alpha. Okay? Well, let's think about the even and odd properties here. Well, cosine of negative alpha, cosine is an even function, so cosine of negative alpha is equivalent to just cosine of alpha. Sine of negative alpha, well, sine is an odd function, so we can move that negative out front, times the cosine of alpha, again, because cosine is odd. Okay, cosine is even. Sine is odd, so we can move that negative out front. So instead of a plus a negative sine, how about I just do a minus sine of alpha? I'm just using the even and odd properties here. Okay, so what do we have here? Well, think of this as over 1. I can multiply the cosines together, just doing fraction multiplication. And this minus sign can be really moved wherever I'd like. This is the same thing as a negative cosine squared of alpha over a sine of alpha minus a sine of alpha. Okay? Where to go from here? Well, the only thing I could see that's screaming for us to try and do here is to add these fractions. So let's put this over 1. We need to find a common denominator. The common denominator will be sine. So we'll put a sine of alpha over a sine of alpha. Okay, let's see where this leads us. Okay, I'm going to erase a little bit of the board we have up here. So let's erase this. Okay, where does this lead us? Okay, well, we'll have a negative cosine squared of alpha minus a sine squared of alpha all over a sine of alpha. Okay. Well, what to do here? Well, I have a minus cosine squared and a minus sine squared. This will actually turn out to be a negative one. Why? Well, think about factoring out that negative. So this is the same thing as a negative times the cosine squared of alpha plus a sine squared of alpha all over a sine of alpha. Well, cosine squared plus sine squared is the same thing as 1. So this is the same thing as negative 1 all over the sine of alpha. 1 over sine is the same thing as cosecant, so this is negative cosecant of alpha, which is the right-hand side. Fun. And we're finished. And we are finished. Okay. Let's see here. I think I have 2 more good examples to do. Just get us a lot of practice. Okay. Let's say we have a secant squared of x plus, how about a tan squared of x? And we want to show that this is equivalent to a secant to the 4th of x minus a tan to the 4th of x. We want to show that these are equivalent. Go ahead and pause the video and give this one a shot on your own before we do it together. Okay, let's go ahead and do this. Now, starting with the left-hand side or the right-hand side, what's begging me, or what's immediately what I'm seeing here, is this right-hand side looks a lot like a difference of squares to me. So I think I'm going to work with the right-hand side on this one. So let's start with the right-hand side, which is the same thing as a secant to the 4th of x minus the tangent to the 4th of x. For me, this is begging for me to do a difference of squares factoring. Okay, here this is a sum of squares. Okay, and I guess you could use a Pythagorean identity over here, but what's really throwing me off about this problem is these 4th powers. So immediately I'm drawn to those 4th powers, and specifically this minus sign is screaming at me that this is a difference of squares. So notice here that this is equivalent to the secant squared of x all being squared minus the tan squared of x, again, all being squared. So this is a difference of squares pattern, and this will expand, or this will factor to a secant of x minus a secant squared of x minus a tan squared of x times a secant squared of x plus a tan squared of x. Okay, cool. Well, we're trying to show that secant squared plus tan squared. We're trying to show that this entire thing right here is equal to secant squared of x plus tan squared of x, which is kind of, looking at this, means that this piece is probably just 1. And I guess there's a couple ways you could think about why this piece here has to be 1. You could write everything in terms of sines and cosines. You could find common denominators, you could add them, but I'm immediately drawn to thinking about a Pythagorean identity with secant squareds and tan squareds. So let's see. I think we have that tan squared of x plus 1 is equal to secant squared of x. So this is one of those Pythagorean identities. And notice, if I subtract tan squared from both sides, that 1 is equal to secant squared of x minus tan squared of x. So what we have right here is equivalent to just 1. So this is just the same thing as 1 times secant squared plus tan squared. Secant squared of x plus tan squared of x, which is the same thing. As the left-hand side. And we're finished. But maybe you didn't notice this Pythagorean identity here. So, I mean, you probably would have had to use a Pythagorean identity at some point, but just for fun, let's take a deeper look at secant squared minus tan squared. Well, secant squared is the same as 1 over cosine squared of x minus, well, this is what? Sine squared of x. Sine squared of x over cosine squared of x. Hi, Pumpkin. Hi, love. So cute. Hold on. Just be right back. Okay. So notice here, my daughter always likes to come in and join in. So notice here we have a common denominator, so we can subtract across the top. This is the same thing as a 1 minus sine squared of x all over a cosine squared of x. And 1 minus sine squared. 1 minus sine squared is the same thing as cosine squared of x all over cosine squared of x. And these cancel to just give you out 1. So either, writing this in terms of sines and cosines and then realizing it's 1, or looking at the Pythagorean identity with tan squareds and secant squareds would also lead you to the same thing. But either way, we have that the left-hand side, or the right-hand side and the left-hand side are equivalent to one another. Fun. Okay. Let's do one more. Okay, this will be the last one we do. So, cosine of theta over 1 minus sine of theta is equal to sine of theta minus cosecant of theta all over cosine of theta minus cotangent of theta. Go ahead and pause the video and try to show that these two trig expressions are equivalent. Okay, let's do it. So what side to start with is really completely up to you. Maybe you are looking at this left-hand side and maybe you're thinking, oh, conjugate trig, conjugate trig, conjugate trig. Well, I don't know, maybe we could try it, see what happens. So if we start with the left-hand side, let's see where this will lead us. Will it lead us anywhere nice? Well, we have a cosine of theta all over a 1 minus sine of theta. Maybe a conjugate trig will be nice here. We'll see. Okay. Well, when we multiply these together, we're going to get a cosine of theta times a 1 plus a sine of theta. And if we were to expand or FOIL out the denominator, we would get a 1 minus sine squared of theta. Okay. Well, I guess what can we do from here? Well, 1 minus sine squared is the same thing as cosine squared. So cosine of theta times a 1 plus sine of theta all over, this is the same thing as cosine squared of theta. And one copy of these cosines cancel. So this is the same thing as a 1 plus sine of theta all over cosine of theta. Okay. Well, that's something to think about. I'm going to leave ourselves a little bit of room here. So I'm going to kind of erase what we have here. So the left-hand side, kind of keeping our work over here. The left-hand side is the same thing as a 1 plus a sine of theta all over a cosine of theta. So this is still the left-hand side. You massaged it to look like this. Okay. And I guess you could distribute this cosine to each piece. So this could be the same thing as 1 over cosine of theta plus a sine of theta over cosine of theta. Well, 1 over cosine is the same as what? Secant of theta, and sine over cosine is the same thing as tan of theta. And I can't really see what else to do with this left-hand side. So, I don't know. If we started with the left-hand side and got here, there's really not much more we can do here. So, I don't know, maybe we start playing around with the right-hand side. Maybe you started just playing around with the right-hand side to begin with. Okay, so we kind of hit a dead end with the left-hand side. Okay, what can we do with the right-hand side? Right-hand side. Okay, so this side right here. For the sake of room, I won't rewrite it down. But at least noticing the right-hand side here, at least I notice I can write cosecant and cotangent in terms of sines and cosines, so this might be something useful to try. So sine of theta minus, well, cosecant is the same thing as what? 1 over sine of theta all over, what we have a cosine of theta minus, what would that be, a cosine of theta all over a sine of theta. Okay, so we want to find a common denominator here and add the fractions. What I'm going to do here is we have this complex fraction, so I highly encourage you, hit this with a sine squared, a sine over sine, hit this one with the sine over sine, find a common denominator, add the fractions, flip, multiply. But what I'm noticing that I can do here instead, since I'm looking at all these denominators have signs in them. So I'm going to just multiply the entire numerator by sine of theta and the entire denominator by sine of theta. Okay, just another way to clean up complex fractions. Complex fractions are fractions within fractions. My computer just went into sleep mode. Okay, so this sign can distribute into these parentheses, and this sign can distribute into these parentheses. So what are we going to get? Well, we'll get a sine squared. We'll get a sine squared of theta, what, minus 1. Minus 1. All over, and what are we going to get? We're going to get a sine of theta times a cosine of theta minus a cosine of theta when I distribute in that sign. Okay, well, what can we do here? Well, I know that a sine squared of theta minus 1. What is sine squared of theta minus 1? Well, if we think about sine squared plus cosine squared of theta, well, that's equal to 1. So if you want, you could replace sine squared with 1 minus cosine squared. Or so a sine squared minus 1, I could subtract the 1 over. Sine squared of theta minus 1 would be equal to a negative cosine squared of theta, just kind of moving those pieces around. So this piece here in the numerator is the same thing as a negative cosine squared of theta all over. And what I'm going to notice here specifically in the denominator is that we have a common factor of cosine that we can factor out. So we can factor out that cosine of theta. And what will we be left with? We'll be left with a sine of theta minus 1. A sine of theta minus 1. Okay, well, where can this lead us? Well, it looks like these cosines can cancel each other out. So we're left with a 1. We're left with a minus cosine of theta all over a sine of theta minus 1. Oh, that's starting to look a lot like our original left-hand side. Okay, well, what can we do here? Let's just move the negative. Or, if you don't like that, just multiply top and bottom by negative 1. So either I can move this negative to the bottom in the denominator, which will flip the order of subtraction, or just multiply top and bottom by negative 1. That'll work. So then we're going to get a positive cosine of theta. And in the bottom, I'll get a minus sine of theta plus 1. Or how about we just write that as a minus 1 minus sine of theta. And that's equal to the left-hand side. This is equal to the left-hand side. We're done. Maybe for fun, maybe instead of turning this cosine squared of theta minus 1 into a negative cosine squared, maybe you saw something different. Maybe you thought to factor. This looks like a difference of squares pattern. Maybe you saw that the numerator was the same thing as a sine of theta minus 1 times a sine of theta plus 1. And in the bottom, you can factor out a cosine of theta. And we'd be left with a sine of theta minus 1. And you say, oh, look, these cancel. So you would be left with a sine of theta plus 1 all over the cosine of theta, which we already showed that the left-hand side was equivalent to. Or you could distribute this cosine to both pieces and show it's the same as secant of theta plus tan of theta. You could have taken this route and just said, hey, the left-hand side and right-hand side both simplify to this, so they must be equivalent. So left-hand side is equal to right-hand side. That one was a lot of fun. A lot of kind of left-hand side is equal to right-hand side. A lot of fun different approaches you could take. Anyway, make sure to get a lot of practice with these. This type of skill of just massaging one thing to look like another thing is a very important and a very useful skill to have. I would say one of the skills that really helped my algebra when I was learning was this exact type of exercise. Where, or anything you have to do with trig functions or trig expressions. It's just the exercise of having an answer, your answer, and then looking at the answer in the back of the book and saying, gosh, is my answer wrong? Are these equivalent? And then massaging my answer to look like the book's answer, or massaging the book's answer to look like my answer, be like, oh, our answers are correct. So anyway, get lots of practice with this in the homework, and we'll see you in the next video. Go ahead and take care.